Hi everyone, thank you for joining us for today's webinar, How to Get the Best Precision and Improve Point Cloud Accuracy. I'm Jeff Bestbrode, Marketing Executive within the Survey and Mapping team here at OxTS, and presenting the webinar today is Jacob Amaker, who is one of our product engineers. During the webinar, Jacob will talk about some of the ideas and things that we have learnt and developed to help you achieve the most precise point clouds possible. The session will cover several key topics, including why IMU and GNSS accuracy is important for point cloud precision, how using bore site calibration can have significant benefits on point cloud results, why using accuracy diagnostics to estimate the uncertainty in point precision is key to survey decision making. The presentation is due to last approximately 45 minutes or so, and there will be some time for questions and answers at the end. If you would like to ask any questions during the presentation, you can ask these using the drop-down menu, which is located at the bottom of the panel on the right-hand side of your screen. If you ask any questions here, we'll do our best to answer them at the end of the presentation. The webinar will also be recorded and a copy will be sent out to everybody who registered tomorrow. So yeah, without further ado, I'll hand you over to Jacob.
All right, thank you, Jeff. Thank you, everybody, for joining. So, as Jeff said, essentially, we're going to be looking at some things that contribute to the accuracy and precision that you might see in a point cloud in a LiDAR survey, although these things would generally apply to all surveys, all technologies, but we're going to focus on contributions to the navigation data, so the INS accuracy. We're going to talk about, as Jeff said, so IMU accuracy, GNSS, the combination of these, combination of other data streams, bore site calibration, processing options, and estimations of position uncertainty in point cloud positions. We're not going to be talking about the surveying device itself, and I'll explain as we go through kind of why that is, but of course we make the INS devices, but there is a good reason to focus on the navigation data rather than the survey data. So to get started, what is georeferencing? So georeferencing is essentially an essential step for dynamic surveys, so surveys where you're moving in some way. So as I said, the navigation data is the biggest contribution to the overall uncertainty of positions of surveyed points in some data in a dynamic survey. So you wouldn't have that in a static survey. You would just be looking for the highest quality surveying device. But with a dynamic survey, you have to combine each frame of data, as you see on the left, with navigation data. So with time, with position, latitude, longitude, altitude, and also its orientation at that time. And when you pair up all the frames with their respective navigation data packets, you can get something that looks like this. And we're going to talk about a number of contributions to the accuracy in something like this. So just to start, we're going to be focusing on INS technology, talking about the IMUs and the GNSS, but I just want to ask, for those in the audience, what kind of devices are you currently using, and what are you interested in using? And I'll kind of frame what I talk about based on this. So the options, you got INS, which would be the kind of integrated IMU with GNSS. You got SLAM, which would be essentially using the LiDAR itself to pick out features and to navigate based on that. You've also got IMU plus a GNSS system, so two different systems that are not tightly integrated, but just using the 6 axes from those. And there are some various other methods. Okay, thank you for answering. It's quite a lot. Thank you. Okay, so to start with, we've got IMU accuracy. So IMU stands for Inertial Measurement Unit. And it's essentially going to be measuring intrinsic acceleration. So it's got accelerometers, gyroscopes, measuring the linear and angular accelerations. And what you can do is integrate these measurements that it's taking to get the velocities and ultimately a trajectory. And so you'd get a specification of an IMU that's maybe something like this. So this is actually what we have on our XNav 650 INS device. This is the IMU inside it. But down here, what we have is a roll and pitch accuracy and a heading accuracy. Now this is not intrinsic to the device because it has no way of constraining its roll, pitch, and heading to what is correct. But what it does have is essentially a random walk. So probably the most important thing to think about the IMU is what is its stability and how well does it measure the intrinsic accelerations that it experiences. So all measurements of all instruments are going to have some kind of error, and that is the most important thing to consider with the IMU. So the IMU accuracy is extremely important. Now, what's actually most important is actually that value at the bottom there, the roll and pitch and the heading, which you get from integrating an IMU with the specifications there with the random walk, with something that is able to constrain one of the angles, for example. So I'll talk about that later, but GNSS, which you integrate with the IMU, is able to constrain the heading and localize the position so it knows that it isn't moving when it isn't. So the IMU accuracy is most often the bottleneck in surveying accuracy, and this is why we're not going to talk too much about, say, different specifications of different LiDAR, because this is the ultimate bottleneck in most surveys, unless you're paying for the very high grade IMUs. So IMU error, it's often not so prominent in surveys when you're just, say, driving past. So if you just drive down a street, you're going to notice it, but not as much as if, say, you drive around a building or an object of some kind. You're not going to see the full error of the IMU kind of making the point cloud blur. And I'm going to show some pictures of this later. But if you see this very simple diagram here, essentially what you're doing is you're trying to survey objects, and in every measurement of those objects, you're going to have some kind of error. And largely this is going to come from the IMU accuracy. And the reason is because you're observing things over some distance. So I've got a quick approximation here. So a 0.1 degree error in an axis at 50 meters, which might be a typical surveying range, is going to give you something like 10 centimeters of position error in that object. And so you can see, if you compare that to, say, a typical LiDAR specification that might be 1 to 3 centimeters accurate, you can see that this is clearly the bottleneck. So moving on to GNSS. So this would be the second major component of most INS devices and most navigation data requiring setups. It's just the chief position localization method out there. There's nothing that can really compare to it outdoors at this point. As long as there's view of satellites in the sky, GNSS is going to be the greatest way to navigate at this time still. And so we're going to just think briefly about what it's doing. So we're not going to talk about the details of it, which can get extremely complicated, as you might imagine, with satellite signals. But essentially, each GNSS receiver is going to have a different specification in that it can receive different signals. So there are a number of different constellations of satellites up there. So you've got Galileo, Beidou, GLONASS, GPS, QZS, and some other things that you can make use of. And each one of these, there are different signals. So there's a lot of different things to consider. But also the way that these signals are processed are different to get that position localization. And so you do need to get a very good view of the satellite. So it's using the satellite signals, it's using the timing information to localize the position down to just centimeters. So it's very heavily dependent on getting the right signals. So one very significant factor are the antennas that you use, of course. So the antenna quality goes without saying. The distance between antennas is very important because that is used for heading accuracy. You can imagine you've got the positions of two antennas and you're using the baseline, you're using the line between those to kind of pin down what your heading is. And the heading is very important because that's going to stop the IMU random walk from just drifting away. So you need to consider all these things. So just a note on kind of the difference that different constellations can make. So on the right, you can see this picture. So you've got red, which is a GPS and GLONASS trace, and you've got blue, which is just a GPS trace. So essentially what's happened here is this vehicle carrying an INS has gone down this road. There's tall buildings and trees blocking signals from the satellites. And you need a certain number of satellites, let's say 6, to get a good stable lock on your position. And with using just the GPS constellation, so there'll be 24 satellites up in the all around the Earth, you might, going through this section, as has evidently happened, lose sight of some of those satellite signals, and the INS needs to work out what to do, essentially. So it's going to have lost a position lock, and its position is going to start to drift. It could be some meters, depending on the conditions. But when you've got GPS and GLONASS, you're looking at 2 constellations, and even with some of the signals being blocked by the trees and the buildings, there are enough satellites still in view to keep a continuous position lock. So you get that nice smooth curve there. And a lot of INS devices now will typically use these 4 constellations. So you've got GPS, the American, GLONASS, Russian, you've got Chinese, and the European satellite constellations now. So an INS system, so what an INS system is essentially going to do is take those 2 major components, the IMU and the GNSS, and combine the data streams. We're going to talk about how it might combine the data streams, but essentially it's using those 2. And these 2 really play to each other's strengths and weaknesses. So the GNSS is going to help give a lock on the heading, so where the INS is directed, and also the position. So it's going to stop that IMU's random walk. Say in this picture here, if you only had an IMU on this vehicle, it would generally register that the vehicle is moving in this direction, but it would randomly be moving to the left and the right. But GNSS is able to constrain it, telling it no, it's actually on the road. So those measurements they're moving left and right are to be discounted. Likewise, GNSS, especially in urban environments, can move around quite significantly, as you can see on here. So you've got signals bouncing off windows, and they're essentially adding path length to the signals. And when it gets to the antenna, the INS is going to read the signal as coming from a satellite, which is some meters further away. And that's going to stop you automatically getting the centimeter level accuracy that you would want in a point cloud survey, for example. So the IMU is able to constrain the GNSS, and the GNSS is able to constrain the IMU. So they really work well together, and this is the typical way an INS system is built. So as I mentioned, there are a number of ways that you can combine the data streams, and there are a lot of intelligent different things that you can do. So at the bottom here, you can see it's a screenshot from our software nav config. So you're able to just put in a very simple parameter, which is where the INS is in relation to some axles rather on the mobile mapping vehicle. And just that parameter is able to significantly increase altitude accuracy, particularly, and also heading accuracy, just by using that parameter and working out what the implications of it might be for IMU drift, for example. There are many other things. Another example is our navigation engine GXIX. So this is taking the raw satellite data and it's able to combine it in an intelligent way, which essentially improves performance dramatically in poor GNSS environments. So when you've got those satellite signals dropping out, you're able to get a position lock much quicker, and in general performance is going to significantly improve. So here's another example. So something that INS systems will typically do is process the navigation data forwards in time and then backwards in time, because in general it's time agnostic, time direction agnostic, and then it will combine those two. So when you go through something like a tunnel, you can imagine the GNSS is working up to the entrance of the tunnel, then it's gone, you can't see the satellites anymore, and so you're relying on the IMU, and that's got its random walk, so you're going to start drifting away. And so the accuracy of the navigation data is going to decrease all the way until you get to the end of the tunnel, when it will be at its maximum before you get a GNSS position lock again. But you can imagine if you process data backwards, the highest accuracy is actually when you're exiting the tunnel, and the lowest accuracy is when you're coming out of the tunnel. So you're able to process it both ways and then combine them in some way. Now, this presents a problem when the processing is not able to tell which direction, the forwards or the backwards, is the most accurate, and it will start to jump between the two. So you can see on the left here, it's impossible to tell which is more accurate, the forward or backwards, and so it's constantly jumping between the two, giving you some jumps. But then in our advanced smoothing algorithm, it's able to just smooth that out completely. So that would be very important for something like a object recognition application. There are additional data streams. We won't talk about LiDAR SLAM, but there's a significant one where you could input even into the INS data processing data from a algorithm that's processing the actual LiDAR view itself to stabilize position. But here we've got an example of wheel speed. So a wheel speed sensor has been attached to a car and it's been driven around this neighborhood. So what you're seeing on the left here is a neighborhood where we've driven clockwise around here, and where you can see a lot of red, the GNSS has been deliberately turned off. So there's no satellite signals. And this point cloud is colored. We'll talk a bit more about this later, but this point cloud is colored by the accuracy, or rather the uncertainty of point positions. So just a number of things to point out. You can see that blue, which is the highest accuracy, is mainly on the road, which is closest to the actual device, and then goes to dark green and light green. And you can see that as you get further away from the INS, you're getting less accurate points. So out here it's yellow, even out here it's getting a bit orange, and that's exactly the IMU accuracy from that diagram earlier, the simple accuracy where the error is multiplied by the range. So the further away you are, it's essentially proportional to the range. But you can see over here, the error is very high because there's no GNSS, so it's relying entirely on the IMU as it's gone through here, and the IMU is drifting fairly quickly as they do. And then afterwards, you can see after using a wheel speed, there's significant improvement. So a wheel speed is able to maintain a constraint on the IMU drift by essentially telling the INS that it's not drifting in that direction because it's going at this speed. So by using this additional data stream, you're able to get a much more usable point cloud. So before, almost all of this data would be unusable, and now you can see it's even reaching some of the highest accuracies just because it's got the wheel speed but still no GNSS. And it improves generally the point cloud, so you can see there's more blue throughout the point cloud, implying a much higher accuracy. This is just another view, so you can see here GNSS has been turned off, and very quickly it's got into red, which would be the kind of highest inaccuracy threshold. So it's like about 0.5 meter plus of point position error. And you can see, say, the house there and the tree there, you can see the drift and the improvement to the clarity of the point cloud just using an extra data stream to constrain the IMU. So something else to talk about is a calibration between the coordinate frames of the surveying device and the INS device. So this applies to all dynamic surveys where you've got a navigation data device, even ones that are integrated. So you can buy some systems out there that have combined an IMU with a LiDAR or a camera or something like this. They have to calibrate very precisely the orientation between that IMU and the LiDAR. And as we mentioned before, with the tiny errors in the IMU angle accuracy and how big a difference that makes to the resultant point cloud, the exact same thing applies here. It's the exact same principle. So you can imagine you've got errors between the two devices. This is going to carry on into the point cloud, as I'll show you. And just one point to make is that it's very difficult to do this calibration because you're talking about points of a degree. It's very, very fine errors that need to be taken into account. So just to show you exactly what the problem might be, essentially when you survey an object from different perspectives, you're going to get a different view of the object. And the bigger the error is between the coordinate frames, the bigger the difference might be. So on the left here, it might look exaggerated, but with the tiny errors resulting in quite large displacements in objects, you can easily get things like this where, say, a lamppost actually appears as a perfectly normal lamppost, but in different locations, or it would actually be a bit skewed as well. And this building, for example, there's the true building, and then two different perspectives. And as I mentioned at the start, what you're doing with the dynamic survey is taking each one of those frames, so the blue and the red are different frames, pairing them with some navigation data, and then you're putting them together. And of course, if there's an offset, like there is here, you're going to get blurring, essentially. And those lampposts are going to blur into, well, it might be a mess, or it might be a very blurry lamppost. And I'll show some examples of this. But the algorithm that we have produced, so it's just in our OxTS georeferencer software, it just takes some small survey data. So you can see on the right here, perhaps wasn't the best picture to show it in the snow, but that's a boresight target. So you just got this square reflective target. You just drive around or fly around if you're on a drone, getting a view of these targets. And then you go into georeferencer and you just let georeferencer do the work, essentially, and it will calibrate the angles between the two devices, as you can see, say here, to points of a degree that you wouldn't easily be able to do by eye or by other methods. And I'll just show you here. So this is 2-point clouds. So this is actually those targets that I just showed. These are reflective strips on our airfield, and you're just seeing reflective objects in the point cloud here. So you can see this is entirely error due to a boresight misalignment, essentially. So what you should be seeing here are two square targets, but you can see they're actually very messy. But after applying the boresight calibration, you can see that the angles are sufficiently calibrated to give you what you might expect. So just some examples. So this is a drone survey, although it looks like a big mess. So there's a car, or there might be two cars, there's a van, and there's kind of an amorphous mess of points here. But after applying the calibration, and this was done in good faith, so the person who had done the survey had put their device on their drone and measured the angles as best they could. They were getting data like this, and this is quite a common thing, so people don't understand just how precise the calibration has to be between the two coordinate frames. But after doing the calibration, you get something like this. So these are the two the boresight targets down here. Here's another example. I like this example. It shows you exactly the same concept as I mentioned earlier, with the range, or rather the error, being proportional to the range. How far away you're looking, you can see it's exactly proportional there. So what you're seeing is a cross section of a road. So we've driven down the road and then turned around, and you're seeing the blue and the red where you've gone east and then west. And this is before calibrating. So as I kind of showed in that diagram before, where you've got two different perspectives, so the vehicle is in two different directions, and you're seeing two different kind of iterations of this building here that is getting more inaccurate with range. But after applying the bore sight calibration, you can see the perspectives are aligned, as you would hope. So something else to mention is the accuracy estimation that INS devices are capable of. So in handling the data streams that are coming in from the GNSS and from the IMU, the INS is able to estimate different accuracies in a number of different parameters. So I will just show this here. So this is some data. You can see where we've driven around here and then come all the way back. This is with a Survey Plus. And you can see what is on here. A heading accuracy is this blue. Pitch accuracy is this black down here. And you've got an east or and you've got a in green, you've got an altitude accuracy. Okay, so you've got 4 things on here that you can analyze and see exactly what the INS is predicting the accuracy of them are. So you can see that, say, heading, although it's got a few spikes, it's coming down here between 0.04 and 0.07. It's where it's kind of resting at throughout the survey. And then you've got a pitch accuracy, which is getting kind of between 0.01 and 0.02 throughout the main part of the survey here. And you've also got the position accuracy. So if you look on the left here, you can see the altitude. Let me just check which one was altitude. So altitude is green. So you can see that that's at about 2 centimeters throughout the entire survey. And position accuracy east is at about 1 centimeter or better throughout. Maybe something like 7 millimeters throughout. This is a very good way to troubleshoot your data and to understand what you're looking at when you're actually looking at your point cloud. And I'll show how this is directly used in a point cloud. But just to mention, you can see here this big spike. Now, if you look down here, this is where the INS has traveled through. There's actually a forest here. You can't see it on the map, of course, but there is actually a forest here. So what's happened is the GNSS signals have been lost, and the INS is having to rely on the IMU, which is drifting. And so you can see that the position accuracy is spiking up from 2 centimeters to 20 centimeters momentarily before going back down, going through this town here. There's a town right there. So you can see all the different kinds of ways this might be used, and there's really no end to the number of different parameters that you might want to look at and analyze. But I want to show now how this is actually used. So we try to make best use of these things as we can. So in our software OxTS georeferencer, which allows you to produce point clouds with a number of different LiDAR and our INS devices, it's going to fill one of the scalar fields in the LAS file with data on the position inaccuracy of points. So for example, you can see in this road survey where it's blue on the road, and then it's green, and then it gets yellow further away, and then orange. So you can see exactly how the IMU accuracy plays an integral role in getting the most accurate point clouds. But if I just show you, let's have a look. Yes, so this is that survey that I just showed there. And now I'm going to try to show you exactly why this might be particularly useful. So this is a road survey, but you can see as the vehicle has traveled under this patch of forest here, you can see, as I was mentioning earlier, about losing GNSS signals in the tunnel. When it's come down here, it's lost GNSS about here, and it's starting to drift. The IMU is drifting, and then it's most inaccurate when it's coming out of the forest before getting the good position lock again. And you might use this for a number of different things. You might want to edit out the inaccurate points, so you would be able to do that. So if I show you here, you'll be able to just remove all inaccurate points if that's what you wanted to do, or you could just go back, resurvey. You could, for example, turn around and survey the other way, and that would give you more accuracy. Maybe get these orange points into green, and you can remove the inaccurate points after that. So that would be how you might use those. So we've got a number of different things that you can look at for further reading. I'm not sure if Jeff is going to put this in the chat, these links here, but you can easily find these on the website. If you just go to the georeferencer page or the XNAV 650 page, for example. We've also got an article on this topic that you can just search for on the website. And yeah, please do follow us on social media, on LinkedIn. We do have Twitter, and also we've got a YouTube channel with some various videos on there. So I think we have some time for questions now.
Yeah, thanks, Jake, for that presentation. That was great. So we do have, yeah, like Jake mentioned, some time for some questions. So if you'd like to pop those in the question field, we'll get those answered for you. We do have one question that's come in already. So does the boresight process work only with multiple LiDAR like Velodyne or Ouster, or is it possible to use with a normal profiler like the ZNF 9012 or the ZNF 5016?
Yeah, so at the moment, the georeferencer software is compatible with essentially the LiDAR ranges of Velodyne, Hesai, Ouster, and we'll shortly be releasing Livox. We have not done the ZNF. We have worked with ZNF LiDAR, but we don't include them in georeferencer because essentially the ZNF software is able to produce its own point clouds using our INS data. So we don't touch ZNF. We might look into including them if we think there is a significant enough reason, but ZNF have their own software that will process that. So in terms of the in terms of boresighting, it's not compatible with georeferencer. The boresight is in georeferencer, but we might consider putting ZNF in just for the boresight if there's a significant demand for it.
We've had another question come in. So is the software compatible with ROS or robot operating systems?
So we haven't done any, we haven't made a release that will, we haven't made any changes from our previous ROS integration work for georeferencer and LiDAR integration at this time, but we're looking into it.
So is in georeferencer, is it possible to apply local coordinate transformation like German, France, or US local datum?
So at the moment, georeferencer will output a LAS file in local coordinates, but this doesn't mean that the final point cloud can't be analyzed in a datum. What it does mean is you have to convert the LAS file into the datum, we do have on our website an article that describes how to do that. So georeferencer will always output it in local coordinates, but you are able to transform it into various datums.
Thanks, Jake. I can't see any more questions coming in at the moment. We do have a few minutes left, so if anybody does have any other questions, yeah, feel free to ask them now. If you do think of any questions after the event, then you can use the info@oxts.com email address, and we'll get those questions answered for you. In terms of the brochures that Jake mentioned, these will be sent out with or links to download them, should I say, will be sent out with the webinar recording tomorrow.
Okay, thank you everybody. Thank you, Jeff.